That's a miracle.
All right. So I think we left off at 37 last time. So let's talk arithmetic sequences. Which of the following on my screen is an arithmetic sequence, Patrick?
Oh.
One of them is, one of them is not.
Would it be number one?
Yeah. In other words, any sequence that has a common difference is an arithmetic sequence, regardless of what its first term is. Now, this goes 4, 4, 5. That is not an arithmetic sequence. It has to be exactly the same difference between every two terms. Now, if I want to list the general explicit rule for an arithmetic sequence, do you know what that is, Patrick?
I know, but I forgot the rule for it.
There's the general rule for an arithmetic sequence, and then for a specific arithmetic sequence, you have an explicit rule for that sequence. But this covers all arithmetic sequences. And notice how it applies to this one that I have written here. What's the common difference?
2.
If I were to say, what is the third term, we can see that it better come out to be 5. What's a sub 1?
That's 1.
What's n?
Yeah, I forgot.
Right there.
Oh, so 3 minus
Yeah.
1.
So we end up with 1 plus 2 times 2, or 5. And sure enough, we can see that the third term of that sequence is 5. Okay? So, if we were to take this sequence right here, the one I've written, and figure out what the specific rule is for this sequence, then I would say a sub n is equal to, the first term is 1, plus the common difference is 2, and this would apply, this rule right here, and I can reduce this a little bit. In other words, I can simplify it by getting rid of the parentheses. So I would say the specific rule for this sequence that I've written here, 1, 3, 5, 7, is equal to 2 times n minus 1. What would the seventh term of this sequence be? In other words, what would a sub 7 be?
Let me figure it out.
Look at the thing I have circled. That's the only thing you need.
Oh, so 13.
Right. And if I were to figure that out, it's 9, 11, 13, that 1, 2, 3, 4, 5, 6, 7. The seventh term is 13. So if I were to ask you what is the 39th term, what is it? Do you have a calculator in front of you?
Yeah, I'll get him one. Hold on.
You always want to have a calculator handy.
These here. All right, there you go, Patrick. I got one. He just got it.
Okay.
The calculator. So that's your general formula, right?
Actually, this is the specific formula.
Yeah, that's what I
Yeah,
meant.
this
So
is the
stop-
general. This is the general for all sequences, arithmetic sequences, excuse me, and this is the specific for this arithmetic sequence.
Right.
So what's the 39th term?
It'd be 77.
Yeah. That's sequences in a nutshell. It's actually fairly straightforward.
How do you do it, Pat? What do you plug in? Into where though?
To the-
Into that specific sequence? Okay,
Or the
great.
general shit. Or the general. Doesn't really matter.
Okay. So-
Okay.
Specific is-
Let's look at this sequence here. What's the general rule again for a sequence, an arithmetic sequence? And I keep saying arithmetic because there's also geometric sequences which are completely different, and there's power sequences which are completely different. So you have a bunch of different type of sequences. The only ones you're studying at the moment are arithmetic sequences, where every term is separated by a common difference. So you still need the general rule. What is it again?
It's AN equals A1 plus B. And then in parentheses, N minus 1.
What is D in this sequence?
Different.
Is that 6?
And that can be plus or minus. It's plus here. What is A sub 1?
It's 3.
So what is the specific nth term for this sequence?
Would we AN equals 3 plus 6
Times.
and N minus 1.
Simplify that.
Alright. Don't we, to simplify, don't we need a value for N?
No, not really. In other words, what we're going to do is come up with what the nth term. You'll see in a moment. Just simplify that, and we'll see what we get for the nth term.
So would it be 9N minus 1?
Well, it's 3, and then we distribute the 6.
You parentheses first.
Okay? Now simplify that.
You have 6N minus 3.
Yeah. So there is the specific formula for this sequence. Remember, this sequence is one of only many. This is a specific sequence. It begins at 3, and every term after that increases by 6. So now you can answer these kind of questions. In other words, what would the 50th term of this sequence be? Which means, what is A sub 50?
$297.
Good. And that's really it. Sequences are actually pretty easy. At least arithmetic sequences are easy. Geometric sequences get a little harder, and then you end up with infinite sequences, which is about as hard as it gets. That's Calc 3. So sequences can be easy at this level, but hard at harder levels for sure.
So with the explicit rule, is that what we just did? It's the same as the specific?
Yeah, when they say explicit, there's actually two kinds of rules for sequences. There's explicit, and there's another one called recursive, which you're not going to get in Algebra 1. You're going to get that maybe in pre-calc. So when they say explicit, there are still two rules for explicit. There's the general explicit, and then there is the specific explicit. The general is for any arithmetic sequence. The specific explicit is for this sequence. And this formula we came up with is for this sequence. That's not the general for any of them, but that is the way you figure out whatever any term is. Okay, notice that if we wanted the third term, it would come out to be 15. Well, that's 15 right there. If we wanted the fourth term, it would come out to be 21. The 50th term was 297. Well, it's much easier to figure out the 50th term by using that formula than it is to count out 46 more terms. You know what I'm saying?
Yeah.
That's the value of these formulas, is that they allow you to go out a long way on the sequence without having to count it out. I could figure out what the 3,000th term of this sequence was pretty easy using this formula. It would take me all day if I had to count it out.
So, David, we don't have to worry then about the recursive sequence.
I don't think so. In Algebra 1, I don't think you get recursive.
You remember covering it? Recursive? You don't remember? Okay, so yeah, so what we basically are focusing on is the general. Well, we're
The general and the specific.
Yeah.
The general and the specific.
Two formulas for the explicit, one general, one specific.
Yeah. The general would cover any kind of sequence I wanted to come up with. In other words, say I came up with this sequence. Well, the general says that the nth term is the first term plus the common difference times n minus 1. Well, first term is 1, common difference is 3, so this is the specific. This is the general rule. And the specific rule I would be able to simplify into 3n minus 2. So the specific rule for that sequence would be this. But you always start with the general rule. This is what you want to memorize. The specific rule is going to change depending on the sequence. Every sequence is going to have a different specific explicit rule. But if you memorize this, that will work for any arithmetic sequence.
Right, basically the general rule produces the specific rule.
Yeah. Once you figure out what the first term is and the common difference, then you can come up with a specific rule. Notice that you can have lots of different sequences that have different common differences. This common difference is 6, but in the one I just wrote, it's 3. And the first term is different. So the two variables for any sequence, arithmetic sequence, are the first term and the common difference. That's the two things you need to figure out. Piecewise functions.
40.
These look very complicated. They're not as complicated as they look. The best suggestion that I can come up with for analyzing piecewise functions is to always start on the right side. What does that mean? That means if I were to graph this, I'm going to start here when x is less than 3. Okay, x is the horizontal axis, f of x is the vertical axis. Whenever I am to the left of 3, the function is going to be that. So where does that function start?
It starts at 4.
And what kind of slope do I have?
Negative.
So where do I get a second point from to draw this line?
You go down 2 and over 1 to the left.
Remember, I got to have a negative slope. If I went down 2 and over 1 to the left, what kind of slope is that?
Positive.
So I can't be over to the left, it's got to be over to the right. And that's really the way to do it. In other words, draw your point where you think it is, and if you have the right slope, you got it right. If you got the wrong slope, go to the other side. You know what I'm saying?
Yeah.
Okay. So that's our line, but it only goes to where x is 3 with an open dot right there, because it's only when x is less than 3 that this is our function. Now, to do this part here, the bottom part, in other words, everything to the right of 3, where's the best place to start?
At 1.
Actually, at 3. When x is actually equal to 3, what is my function equal to?
Three.
Plug it in. What do you get? Plug in 3 into this function down here.
9x plus 1.
Yeah, that's the function. Whenever x is equal to or greater than 3, this is the definition of our function. Remember, we actually have two functions. Whenever x is less than 3, we've got this minus 2x plus 4. That's the definition of our function. But whenever x is either equal to 3 or greater than 3, we have this bottom function, which is different. So when x is exactly equal to 3, where do I start?
At 1.
Plug in 3 for x in this bottom function. What do you get?
9.
Try again. What's 3x plus 1 when x is 3?
That's 10.
Okay, so that's what x is, that's what f of x is when x is 3. So if I want to know where my starting point is, I go up to 10 when x is 3, and it's a closed dot, because when x is actually equal to 3, I'm 10. I'm not minus 3. What's the slope of this new line?
3 over 1.
This one right here, what's the slope of that? Oh, I'm sorry, you said 3 over 1? So what do I do to get my second point?
You could go up 3 over 1 to the left.
What kind of slope would that be?
Negative.
So which way do I have to go?
To the right.
And it stops right there. So I could put an arrow that direction, and I could put an arrow in this direction, meaning it goes to infinity in both those directions. But there's the graph of this piecewise function. Okay? And notice that you get a lot further if you start with what's on the right-hand side. And then you plot whatever function applies to that area. And then you go to the right-hand side again and you plot the function that applies to that area. So their question here, because this is f of x equals, okay, so when they say f of 3, what is that equal to?
For the top one, it'd be
No, hold on. It's not in the top one. F of 3. The top one only applies when x is less than 3. The bottom one applies when x is either equal or greater than 3. So which function applies?
The bottom one.
And what is f of 3?
P10.
That's the answer. What is f of 2?
Hold on, just gotta write that down. So then f of 2 would be 7.
Plug it into the, don't forget that, here's the first one. Remember f of 2 is this function here.
Right, it's less than 3, right?
So it plugs into a different function. When you plug in 2 to that, what do you get?
You get a
That's it. That's how piecewise functions work. And it's as straightforward as that. Sometimes you have
David,
3 intervals, sometimes you have 4, most of the time you just have 2, but you just have to find where you're at, in other words, what the value of x is, and then use the function that is appropriate for that value.
I missed it, David. What was the answer when you said the value was 2 and we were using the top formula?
Yeah, if you take f of 2, then it's minus 2 times 2 plus 4, that's equal to 0.
Equals to 0. That's what he's got, right.
So what's f of 0?
The rule, hold on for a second, the rule is he actually always has to look at the f of x that he's given and determine where that fits into which...
Exactly. In other words, to figure out which function you're going to use, you have to look to here.
Right, you have to look at that right-hand side.
Yes.
Yeah.
That's always where you want to start when you even think about piecewise functions. Whether you are graphing them, whether you're reading a graph, whether you're evaluating a function, you want to start on the right-hand side. So what would f of 0 be?
be 0.
Try again.
Oh, would be 4.
There you go. I think you get it. They're going to give us plenty more if you don't. So, all right, this one they want us to graph. the x-axis. This is the, it doesn't say whether it's f of x or y, I'll call it y. So, how do I graph this?
You could start at 1 for the top one.
Okay.
And then you would go...
Is that a closed dot or an open dot?
Open.
In other words, when x is equal to 0, we're in that top function. We're only in the bottom function when x is greater than 0. So right here, x is equal to 0, right?
Yeah.
Means it's a closed dot. And what's the function look like?
You could go down 1 over 1 to the would be the right.
Well, if I did that, that's where I would be. There's two things wrong with that. What are they?
X is greater than 0.
Okay, that's one thing. What's the other thing?
It's positive.
Yeah. So which way do I have to go?
To the right.
You meant to the left.
Nope, sorry.
Ah, I'm the one that's confused. Excuse me. You were right the first time. Almost. Now there's only one thing wrong with that. It's to the right of the y-axis. So how do I graph this line and stay to the left of the y-axis? Instead of going down 1 and right 1, what should I do?
You could go up 1 and over 1.
To the left, exactly. Now, if I connect those two lines, there's my function. That is the graph of that part of the function. And it's a closed dot because that's where the less than or equal to is. This one's going to have the open dot. Where do I start the bottom one?
At -2.
Good. With an open dot. What's the slope here?
You could go up 3 over 1 to the right.
Good. Connect those two lines. There's the graph of this function. Notice that this is still a function. It passes the vertical line test. I can pass a vertical line test through any point of this function and I only get one value. Even if I pass a vertical line through this point right here, I only get one value, it's that one. Because that's the closed dot. Then if I go over and pass vertical lines through the rest of it, I still only get one value for y. That means it's a function. All right, let me open up this other page. Okay, there wasn't a lot on piecewise functions.
So, David, on those piecewise functions, is there a list of steps that you take? The first thing that you address, the second thing you address.
I would say start on the right, start at the top, start at the left.
Start at the right.
No, you don't even need to write that down because notice that when you start on the right, you always start on the top. Starting on the top is always starting on the left.
Okay.
So as long as you start on the upper right, you will be starting at the right place. In other words, I started with this function here, which goes from -infinity to 0. After I graphed it, I went down and to the right and graphed this one, which starts at 0 and goes to positive infinity. So that's why I say start on the right, not only on the right, but at the top, because it always defines itself starting from negative infinity on the x-axis. In other words, you don't ever see anything like this.
And some of these actually have three.
That 3 is no problem. That's just 3 intervals instead of 2. In other words, this was 2 intervals. I could add a third interval real easy. But the key here is you don't ever see this. You don't ever see the top function starting to the right and the bottom function going to the left. You always see it the other way around.
Gotcha.
So this is always going to be that. Sometimes you might see that, where the equal sign, one of them will have an equal sign and one of them will not. Notice that if they both had that sign, then this would be a closed dot down here, and that would no longer be a function because you wouldn't be able to say what is f of 0. F of 0 would give you 2 values. It would give you -2 and it would also give you +1. So these piecewise functions only work if one of these does not have the equal sign. Actually, in our problem, it was the bottom one that did not have it. And that's what made that an open dot, not a closed dot. And that's also what made it a function. All right, these are pretty straightforward here. Whenever you're adding polynomials, it's very adding or subtracting, you add like terms or subtract like terms. So what's the answer here?
It'd be 7t squared.
To the third. Yeah, you might need to look on your paper form here. It's hard to read these on mine.
Yeah, I'm going to give them the sheet.
Okay.
And then it would be -6t squared.
Good.
I mean 60.
Good. There's only one t squared. There's no t squared over there, so you just count the one that you see. How many total t do you have?
You have 1, so it'd be +8t.
Plus 8t. And how many total numbers do you have?
You have 2, so that would be -7.
Yeah. And there's your answer. In other words, these are very, very straightforward. So let's change that plus sign to a minus sign. Tell me what that answer would be. In other words, 4t cubed minus 6t squared plus 5. And then I'm going to subtract. And give me this answer.
-1t squared, or t cubed. Then it'd be -6t squared. -8t. And then minus...
You got a negative there, you got a negative there.
So it would be plus 70.
Uh-huh. In other words, whenever you have a negative sign in front of a bunch of terms inside of a parentheses, you have to distribute that negative sign to every term in here. In other words, remember my rule about handling subtraction? Well, we can do the same thing here. Let's change it to a plus, and then change the sign on every term that's inside the parentheses. Now you can get rid of the parentheses. This becomes minus 3t cubed minus 8t plus 12. That's the way you handle subtraction, whether it's followed by a single term or a bunch of terms. Okay? I didn't need to make up problems. I should have just looked at the next one. Is that a minus 3x?
Yes.
Now, you can do that as a first step, or you can just do it on the fly. Whatever you're comfortable with doing, I don't care which. I don't think there's a right or a wrong way, if you can get the right answer.
So would the first one be negative 7x squared? 7x cubed? Yeah, squared. Then it would be minus 9x.
Okay, think again.
Oh, plus 9x.
No? All right, let's go back and do this the hard way. This is a subtraction problem. So let's turn it into an addition problem, and then change the sign on every term that is inside those parentheses, and then take away the parentheses. Now I can also take away that plus sign, because everything has its own sign, so I don't need that plus sign. I can take away those parentheses. They were never needed. Now I've got that gives me minus 7x squared. I've got a minus 3x and a plus 6x. What is that?
3x.
Plus 3x. You can't drop the plus sign when you're in the middle of a polynomial. You got to put the sign on it. And then what is minus 13 and plus 9?
Negative 4.
There's your answer. Now, whether you need to go to those extremes or not, I don't know. You tell me.
Probably wouldn't hurt. She's a big stickler on showing all of your work. So.
Well, that's not necessarily showing your work. In other words, she's not going to care. You could go straight from this step to this step, and she's not going to complain, I guarantee it.
Okay, when you distribute that negative sign across the second parentheses to get rid of it, it changes that negative to a positive? Is that what you're saying?
It changes the sign of every term in there. In other words, it changes the sign of that to a negative, changes the sign of that to a positive, and changes the sign of that to a positive.
Right. And what happens to the negative outside that you distribute? Did that become a positive then between the two parentheses? You see what I'm saying?
Yeah, I do.
What do you do with it?
Well, whenever you have a plus and a minus together, that's equal to a minus. Okay? Right. So if you want to look at it like that, okay, so I have a subtraction problem here, so I'm going to change it to an addition problem, and then I'm going to change the sign of every term, and then I'm going to take away the parentheses. So the only thing I have left is this plus and minus next to one another. That means I can take away the plus.
Okay.
Now, I never did need these parentheses. You never need the leading parentheses. Okay? So once I get rid of those parentheses and these parentheses, now it's just a problem of combining all the terms. The key is the subtraction. When you have subtraction followed by parentheses, you have to make sure that this negative sign is distributed to every term in there. How you do it is just technique. My technique is one way, somebody else's might be another. It results in the same thing. Since I tend to preach to students that in order to do subtraction, turn it into addition, well, that philosophy works perfect here also. You can look at this problem, and there's only one subtraction sign in there if you want to think of like that. That's this one right here. Everything else is a negative sign. So if we turn this problem into a subtraction, into an addition problem, I'm going to make that an addition and change the sign on everything that follows that negative sign, which is to say everything in those parentheses. So tell me what this is. Patrick?
Would it be x? And then it'd be minus 6?
No.
Plus 6.
Okay. In other words, this is the subtraction. If you have to, change that to an addition and then change the sign on that and the sign on that. Everything inside the parentheses has to have its sign changed. At least everything that's being added or subtracted. If you were multiplying stuff, not true necessarily, but and if I had an xy here, yes, I'd have to put a negative sign in front of it, but only in front of the term, not both the x and the y. Okay? So maybe the best way for you to do this is to do this process every single time. I don't know. Let me give you another one.
No, I really think it is, because, you know, that's what I mentioned about her saying that she wanted him to show his work, and I understand you saying, well, that's not really showing his work. But where he gets in trouble is when he tries to carry too many functions in his head, and then he makes mistakes on these very simple problems.
Okay. I agree. There's no downside into doing this I'm not even sure it's the long way. It's maybe an extra mental step, but that's all. So how would I do this, Patrick?
You'd have 2x?
No.
Oh, sorry, 4x.
Okay.
Then would you have minus 3?
Yeah. Now, how you get to this, in other words, you don't really have to show any work to do that. You know what I'm saying, David?
Yep.
Whether you show that other step or not is not material. Most people would never show that step. In other words, I'm not sure you necessarily want to go into your test and show this step right here. You could, I suppose, but most people would not. I would not expect to see this step on an analysis of this problem. Most people would go straight to that's the next step. How you get there, though, is up to you. You can get there however you want. If you want.
That's what I'm concerned about. It might not be a step, but there has to be some process that he knows that he's done it so he can carry it from one place to the other.
Well, there's two ways to look at this. You can think of multiplying everything inside the parentheses by a negative sign, or you can think of it as changing the subtraction to an addition and then changing the sign on everything, and then just dropping the parentheses and the double plus sign. That works also. Either method works. So it's whatever works best in your brain is the way you want to do it. Okay, this is much easier. Multiplication is always easier than addition or subtraction. There's no problems with multiplication. Notice that how hard that subtraction problem was. And subtracting fractions and so forth and so on. Multiplication is easy. So is division. So what's the answer here? What's 5x squared times 3x?
Wouldn't that be 15x cubed?
Yep. What's the next term?
And then it would be 10x.
Hold on, what's the sign? Don't drop that negative sign.
It'd be negative 10x.
Right, because you're multiplying 5x squared times minus 2x squared. That's going to give you minus 10x to what power?
What would it be to the fourth?
Uh-huh. And then finally the last term?
That would be negative 25x to the second.
Very good. Now, what is this if I said write it in proper format?
It'd be negative 10x4 plus 15x to the third, then minus 25x squared.
Right. Proper format, always putting the highest coefficient, the highest exponent first. What is x minus 5 quantity squared?
Isn't that x squared minus x squared minus positive 25 plus 25?
That's the biggest mistake made in algebra. There's two biggest mistakes in algebra. That's the biggest one. This is x minus 5 times x minus 5. How would I multiply those two things together?
You'd have x squared and then plus 25.
No. FOIL it, which is to say multiply every term by every term. In other words, you multiply that times that, multiply that times that, multiply that times that, and you multiply that times that. So there's 4 multiplications that need to happen. What's the first one result in?
You'd have, of course, x squared.
What's the next term?
Then you'd have minus 5x.
The next term?
And then you'd have another minus. Then you'd have another minus 5x.
And the last term?
And then you'd have plus 25.
Okay. Notice the difference. There is a middle term here. There is always a middle term. Whenever you take a binomial term, x minus 5 or x plus 1 or x minus 10, it doesn't matter. If you square it, you're always going to have a middle term. And most people want to drop it. Most people want to say x plus 1 squared is x squared plus 1. It is not. It is x squared plus 2x plus 1. Remember, when you're squaring something, you're merely multiplying it by itself. So this is probably a good thing to do as your first step. And then just treat it like the same way you would treat, if I told you to multiply x plus 1 times x plus 2, you wouldn't even think twice about it. You would FOIL it, right?
Yeah.
Okay, well this is no different. It's just the same term times itself. You still have to FOIL it. Okay. When you have, were you taught FOIL, Patrick, that terminology?
Yes.
I hate FOIL. The reason I hate it is that it doesn't apply to this problem. In other words, FOIL is first, outside, inside, last. Well, that only works if it's a binomial times a binomial. This is a binomial times a trinomial. FOIL isn't going to work.
The FOIL only works for what, David?
For a binomial times a binomial.
Okay, binomial times, okay.
What I prefer instead of FOIL is ET, which is to say every term by every term. In other words, for this problem, I'm going to take the first term, I'm going to multiply it by that, and then I'm going to multiply the first term by that, and then I'm going to multiply the first term by that. Then I'm going to multiply the second term by that, second term by that, second term by that. In other words, every term by every term. So when we do that, what do we get? In other words, I wish they would never even introduce the term FOIL. I wish they would start with ET, and then that applies to everything. It applies to trinomials times trinomials. It applies to binomials times binomials. Works for everything. What's my first term as an answer here?
It'd be 2x to the third. And then you'd have 6x to the second.
Plus or minus?
Plus.
You see why we need to say plus?
Yeah.
Sometimes you need to say it, sometimes you don't. You didn't need to say plus in front of the first term, because the first term wasn't being added to anything. In other words, if I don't write a sign in front of this, it's assumed to be plus. But if I don't write a sign in front of this, then I have this jumble of garbage that doesn't mean anything. That actually would mean they were being multiplied together. So you can't drop that plus sign when it's a term that's being added to another term. Okay, what's next?
And then you'd have, let's see, would you have 2x to the
You know what?
second?
Make sure when you do these that you follow a pattern that is always the same. Don't jump around. In other words, it's easy to get lost and do that one and then that one and then let's see, let's do that one and that one, and now I got to go figure out which one have I not done. You know what I'm saying? Follow a pattern. Do this one times that, and then do this one times that, and then do this one times that, which gives you that minus 4x. Now go back, take the second term times the first. There's another plus 2x squared. The second term times the second. That's another plus 6x. And finally, plus 1 times minus 4, minus 4. Now we can combine all of those. What do we have as a net answer?
We have 2x to the third plus 8x to the second. Then we'd have 2x plus 2x. And then minus 4.
Yeah. Whenever you're doing these, there's always only one of those, and there's always only one of those. In other words, when you go to simplify it and combine it, you don't have to search for all the x to the cubes. There's only going to be one of them. And you don't have to search for a bunch of numbers. There's only going to be that last one. Okay. Greatest common factor. What that means is we want the greatest term that I can divide into both of these terms evenly. What is it here? What's the, let's look at the number first, and we'll look at the variable second. What's the greatest number that can be divided into both 16 and 40?
8.
Okay, so I can factor out an 8. What's the greatest variable that divides into both of these?
X to the second.
Good. I can factor out an x to the second. Now what's left over? In other words, when I actually divide that into that, what do I have here?
You'd have 8.
What's 16x squared divided by 8x squared?
Sorry about that. You'd have 2, just 2.
And then what's 40x cubed divided by 8x squared?
Wouldn't that be 5x to 5x?
That's it. You've just factored out the greatest common factor.
Good job.
All right, factoring. Did they teach you a factoring method, Patrick? Did they call it anything?
No, they didn't.
Good. Half the schools get this thing called the California method, and I hate it. It's confusing, it's complicated, nobody understands it, nobody can use it. My method is much better. My method has 4 steps to it on these simple ones. Now, when you're factoring, this is a quadratic, okay? Most of your factoring problems are going to be factoring quadratics. You might want to write out a list of steps. The first step is to separate the x squared. Separating it into x and x. Making sure that when I multiply these things back together, I'm going to get this first term of x squared. That's step 1. Step 2, figuring out what both of your signs are going to be. Are they both going to be plus? Are they both going to be minus? Are they going to be plus and minus? Are they going to be different, or are they going to be the same? What are these signs going to be?
Since one of them is a plus, one of them is a minus, aren't they going to be opposite?
No. What we use to determine that is we always look at the sign. This sign on the constant, the plus sign on the 42, is used twice in our method of factoring. First of all, we use it to determine what the signs have to be. You cannot produce a plus 42 unless the signs are the same. They either have to both be negative or they have to both be plus. In other words, if let me just jump to a moment here. I was thinking about this earlier. The way to teach this to students is to go the other direction. If I multiply these two things together, what is my constant at the end? In other words, I get x squared minus plus x minus 2x, so that's minus x, and then finally I have a number as my very last term. What's the sign on that number?
Negative?
Yeah, -2, right? So if I start on the right side here, and I'm looking at a -2, I know the signs have to be opposite one another. You cannot produce a -2 unless these signs are different. If they're both negative or if they're both positive, I'm going to have a +2 over there. So that's a very important realization, is that when you multiply two linear factors together, your last term always reflects the signs. So when you're going the other direction, when you start with the quadratic and you're trying to factor it, if I see a +42, the only way I could have produced that is if I either have minus minus, which would produce a plus, or if I have plus plus, that would also produce a plus. The one thing I cannot have is plus minus, because that would only produce a minus there. Okay? Now, so step 2 is I know the signs have to be the same. Now, to figure out whether they're minus minus or plus plus, look to the sign of the middle term.
Pay pay attention to this. Okay. Wait a minute, I got a dog in here, David. I got to get him. Come on.
Because the middle term is minus, they have to be minus minus. Now, that's the second step, okay? Step 1 was separating the x's. Step 2 is to determine the signs. Step 3, factors of 42. Let's start there. How do I get factors of 42? What's the obvious factors of 42?
Hold on for a second, David. I get distracted. But the step 2 is that you need to determine the signs.
Both
right?
of them, right.
Both, okay. And step 3 is what?
Factors of the constant.
Okay.
So let's talk about how we figure out factors of numbers. This is where your multiplication tables is really required. You cannot do this on a calculator. You can't figure out factors of 42 on a calculator. The only way to figure it out, well, is the best way to figure it out is to know your multiplication tables. But if you're in a pinch and you're trying to figure out what factors of 42 are, we'll always start with this, 42 and 1. 42 times 1 is 42. Now, to figure out another factor, I can cut this in half and double the 1. So 2 times 21 is also 42. Now, at this point, I can't cut the 21 in half anymore. So, can you think of any other two numbers that multiply together to give 42? About 7 and 6.
Yeah, because the way we learned how to do these, I just remember this, is that we figured we're supposed to figure out what adds up to negative 13, but
I'm getting there.
What times?
I'm getting there. Okay? First of all, you need to figure out how to factor that 42. Because what you just said is absolutely true. But you have to figure out what multiplies together to give you 42. And that's called factoring the number 42. So, the third rule is factors of 42 that add, because that is a plus, to the number 13. Not to minus 13, to the number 13. So, which of these factors over here add to 13?
7 and 6.
For this problem, it's that simple. Okay?
Okay.
Change the problem slightly. In fact, let me change the problem a lot. Okay? Now, let's start from scratch. Okay? Here's a different quadratic. First step, separate the x's into what?
It would be plus or minus.
Well, when I say separate the x's, I mean break that down into x times x. That's step 1. It won't always be x times x. Sometimes this might be a 2x squared, in which case it would have to be broken down into at least 2x times x. You see? In other words, figuring out what these two terms are involves breaking down that very first term, factoring that first term. Well, in these simple problems, most of the time, this is always going to be x squared, and it's always going to break down into x and x. Factoring starts becoming difficult when you throw in a coefficient here. But there's two kinds of factoring problems. This is the easy kind. And I think this is probably the main one you want to know for your test, is this one. You want to be really good at factoring these kind of problems. So I've done step 1. What is step 2?
You have to figure out what signs go in there.
What are the signs going to be?
would it be minus and minus, or would it be minus and positive?
Well, if it was minus minus, what would this be?
It'd have to be a plus.
Okay, so it can't be minus minus.
So it'd have to be a minus and a plus.
Exactly. In other words, I can either write minus plus, or I can write plus minus, and it's the same thing. It's not going to be any different for this problem. So it doesn't matter which order I write them in for this problem. As long as it's x and x, and you figure out that the signs have to be opposite, then you can put plus minus and be done with it. Now, step 3 is similar. It's not exactly the same as the other problem. In this case, I still want factors of 42, but instead of adding to this coefficient, they need to subtract because that's a negative sign. So this sign that's on the constant not only dictates what my signs are, but it also dictates the third rule. In other words, I don't want factors of 42 that add to 19. I want factors of 42 that subtract to the number 19. Well, what were all my factors of 42? Which ones subtract to the number 19?
21 minus 2.
Okay, that's step 3. Step 4. Assign the bigger factor to the sign of the middle term. So where's the 21 go? Where's the 2 go? Assign the bigger factor.
The 21 would go in the plus, and then the 2 would go.
Say it again. Take the bigger factor.
Oh, sorry.
So state the rule again, David.
The bigger factor goes with the sign of the middle term. 21 is the bigger factor. The middle term sign is negative, so the 21 goes there, the 2 goes in the other spot. So there's 4 steps in some of these. When you have opposite signs, there's that 4th step. Now, this is important, 5th step actually. This is the correct answer, but when you want to check your answer, in other words, after you have factored these quadratics, it's generally a good idea to take a look at whether or not we have the right middle term. I don't need to check to see if we have the right first term. I know we do. I constructed the thing based on the first term. So I know x times x is equal to x squared. I also don't need to check this term. We based our factors on the fact that they were factors of 42. So I know that plus 2 times minus 21 is going to equal minus 42. So there's no need to waste time checking the first and third term. The term that needs checking is the middle term. Well, you get the middle term by multiplying the 2 inside terms and the 2 outside terms. That's the O and the I of FOIL, is the outside and the inside. Well, the inside terms give you plus 2x. The outside terms give you minus 21x. Add those two together, you get minus 19x. If that matches your middle term, you've done it properly. Now I can erase everything. That's my answer. Now, I can't remember. Oh, I made this up. If I said, what is the solution to this equation? In other words, if I had this quadratic is equal to 0, and I've now factored it so that that quadratic is this linear term times this linear term, and they're equal to 0, what's the solution? What is x equal to? Patrick?
Oh, sorry.
All right, let's talk about the most important theorem in all of algebra. It's called the zero product theorem. It says that if you multiply two things together and you get 0 as an answer, one of those two things has to be 0. You cannot multiply 1/2 times 1/10 and get 0. You can't multiply any two numbers and get 0. It's impossible unless one of them is 0. Okay? That's the most important theorem in algebra. So, the reason I factor this quadratic is because I'm trying to get one thing multiplied by another thing is equal to 0. I can now solve this problem by setting these each equal to 0. So I'm going to say, well, that means x plus 2 equals 0 or x minus 21 equals 0. Well, if I solve this equation, I get x equal minus 2. And if I solve this equation, I get x equal 21. There's your two solutions to this quadratic. And quadratics almost always have two solutions. Quadratics have two solutions. Cubics have 3 solutions. Quartics have 4 solutions. Linears have 1 solution. A linear being x plus 5 equals 10. That's only going to have one solution because it's a linear equation and the solution is x equals 5. Okay? This is a quadratic function that I have here. We would expect to have two solutions, and we do. If you only come up with one solution, you probably have made a mistake. Not always. There are certain quadratics that would only have one solution, but most of the time you've made a mistake if you do not come up with two solutions. Tell me what this would be. What are the solutions for x?
Wouldn't that be x equals -1 and then x equals 2?
It's the opposite signs.
Oh, so...
You see why? In other words, to solve this, I have to let x minus 1 equals 0, which means x equals plus 1.
Oh, all right.
And then I let x plus 2 equals 0, which means x equals minus 2.
Oh.
Okay?
All right.
Now, what is the other one that throws a lot of students off is this one. What are my two solutions now?
Wouldn't that just be x equals 1?
Not 1.
-1.
Remember what's the zero product rule of algebra say?
One of them must be a 0.
Okay. Well, you can change that rule to say both of them are 0.
So would it be x equals 0?
Yes. Now, when I said you can change that rule, you can't really, because the rule doesn't say both of them have to be 0. But when we solve it, we do let both of them be 0 to come up with the solution. And then when you get more complicated math, as you get into Algebra 2 and stuff, you will find sometimes where one of these solutions doesn't work. If you plug the solution back in, you don't get 0. And so you have to cross it out. It's called an extraneous solution. And gosh, for years I thought, well, how can you have extraneous solutions in math? Math is so precise. But the rule says that really only one of these things has to be 0. In reality, we let both of them be 0 in order to solve for the two solutions. But only one of them has to be 0. Okay, that's pretty straightforward. What's the leading coefficient and what's the classification of the polynomial?
Well, it's -2x to the third, and what the classification would be. Yeah, crap, I always forget these. Would it be a trinomial?
And it's a good try. It is a trinomial because there's three terms. But that is not its classification as a polynomial. It is a third-degree polynomial because of the exponent of the lead term. If that was a 4, then it would be a fourth-degree polynomial. In other words, if, let's change this just so you don't get confused by what I just said. That is also a trinomial, but it is a fourth-degree polynomial. See the difference?
Yes.
Okay. This is a quadratic that's already been factored. When you have a linear term times a linear term, you're going to end up with a quadratic. Okay? They've already factored this. If I want to graph this, what do I know about quadratics? Well, I know that they are parabolas, right? That's what a quadratic is it's a parabola. It might be a parabola that does this, but most parabolas are going to go through the x-axis twice. Right?
Yes.
Okay. Well, this one has it factored already, so it's really easy to figure out where it goes through the x-axis. If I say that's equal to y, where would y be 0? What two values would y equal 0?
-3 and 1.
Let's plug in -3. It's -6 times -2. That's not equal to 0. That's equal to 12. So where is y equal to 0 again? What makes this 0?
Adding 3.
X being equal to 3. Right? If x is equal to 3, that's equal to 0. And now 0 times this term is 0. So if I want to find where y is equal to 0, I have to set that equal to 0, which is not the same as just reading the sign on that thing. It's always the opposite sign. So when x is 3, this term is equal to 0. Where else would one of these terms be equal to 0?
Would be at 1. Or
plug in 1 for x. Do either term equal 0?
-1.
There you go. So those are my two x-intercepts. Well, if I look at that, I know that if I were to multiply these two together, I start out with an x squared has a plus sign. Which way does my parabola open? Up or down?
Up. Will it be up?
Yes. If it's a plus sign, it's up. So I can graph a good deal of that parabola just based on its x-intercepts. Now, the only thing I wasn't able to graph was exactly where this vertex is. Where on the x-axis is that vertex? Everything is symmetrical on a parabola about what is called a line of symmetry.
So it would be maybe about 2.
Yeah, halfway in between -1 and 3. So I know the axis of symmetry is 2. Well, if I absolutely have to put a coordinate on here, and I really do, because in order to graph a parabola you need 3 points. Well, I have 1 point, 2 points. I need this third point, the vertex. Well, I just figured out what the x-coordinate is, 2. How would I figure out what the y-coordinate is?
You just go down there? Or
Yes, do it.
So would that be about -2 or 3?
Don't guess. Plug in 2 for x.
Oh, all right.
So it's 2 minus 3 times 2 plus 1. What's that equal to?
It'd be 3. Sorry about that. It'd be -1.
Do each one separately. What's 2 minus 3?
It's -1.
What's 2 plus 1?
It's 3.
What's minus 1 times 3?
-3.
Okay. So the y-coordinate of this vertex is -3. And now I have 3 points, and that's all I need. I could actually answer this question without a graph. Is all I need to answer that question are 3 points that are on the graph. Well, what are my 3 points? -1, comma 0, this point here. 3, comma 0, this point over here. And 2, comma -3. If I gave the teacher that answer, she should accept it. Because a parabola is defined by 3 points. If you can give her 3 points on the parabola, there's only one parabola that can be graphed from that. There's not 2 different types of parabolas that can be graphed from 3 points. What's that, David?
You know, I actually had a question, David. Why isn't that, if you've got the 1 point -1 on your number line, the other one is 3, isn't the midpoint actually on the x line 1, not 2?
Yes, you're absolutely right. I made a mistake there. I didn't notice that.
Okay, yeah, so just, did you see where that is?
Yeah, good catch.
Yeah,
I
okay.
apologize. That changes everything, actually. So that means that's 1. Now we have to substitute 1 instead of 2 for x.
Good, now you just do it again.
So what's the y value of the vertex? If the x value is 1, and your dad is absolutely correct, what is the y value? Again, x of 1.
So it'd be -2 times 2. It'd be -4.
Yeah. Thank you, David.
So that's 4. So they saw that one?
Yeah.
Yeah, good.
And that's the way you do parabolas or quadratics. All right. This is a bit of a trick question. Let me start with an easy one. What's the y-intercept?
51. Okay.
It's -3.
Yeah, because the y-intercept is where x is 0, right? So if I plug in 0 for x, I get -3. So what is the y-intercept of this?
-14.
Okay. Give me a polynomial. Oops. Give me a 5th degree polynomial that has a y-intercept of 0, 2.
It's a 5th degree binomial.
Yeah, 5th degree binomial. I'm sorry, yeah. Doesn't really matter whether it's a binomial or a polynomial.
Okay.
The important thing is that you need 2 terms. 5th degree binomial, what term do I have to have?
You have to have a 5.
You have to have an x to the 5th.
Yeah.
Okay? If it's only going to be a two-term expression, in other words, I'm not going to have an x to the 4th, 3rd, 2nd, or x to this thing. I'm only going to have a number. What's the number?
Two.
There's one answer to this question. Another answer? Another answer? As long as this constant is 2, that's always the y-intercept, is that constant. All right, that's probably a good place to stop. I see that
Yep, we're perfect.
the next question changes the context a little bit. And we've gone an hour and a half, so imagine your brain is probably fried right now, Patrick. Is that true?
Yeah, a little bit.
Okay, good.
Yeah, but we had a good session though with this. So
Yeah.
you know, this one was important on the polynomials and stuff like that. I thought we did good on those.
I agree. And I think
All right, David.
Patrick understands this. He had a good session too. I think he
Yeah, I thought so too. I really did. So we'll see you tomorrow then.
sounds good. Talk to you then.
Thanks.
Bye-bye.